Dark energy. The mysterious force which is changing the way we understand the cosmos. Let's start with the basics. The universe, as we know it, began with the Big Bang, a massive explosion that occurred roughly 13.8 billion years ago. After the explosion, the universe began to expand, and matter started to come together to form galaxies, stars, and planets. The force of gravity, which pulls objects towards each other, played a significant role in this process. For a long time, scientists believed that the expansion of the universe was slowing down due to the force of gravity. However, in the late 1990s, two independent teams of astronomers studying distant supernovae found something strange. They discovered that the expansion of the universe wasn't slowing down at all, it was actually accelerating. This discovery was a game changer. It suggested that there was a force in the universe that was driving the acceleration of the expansion. And that force is what we now call dark energy. So, what do we know about dark energy? According to recent measurements, dark energy makes up about 68% of the total energy density of the universe. That's a massive amount of energy, and yet we can't see it or detect it directly. Think of dark energy as the evil counterpart to gravity, an anti-gravity force providing a negative pressure that fills the universe and stretches the very fabric of spacetime. As it does so, dark energy drives cosmic objects apart at an increasingly rapid rate rather than drawing them together as gravity does. Some scientists believe that dark energy is related to the vacuum of space itself. According to this theory, even when all the matter is removed from a particular area, there is still a certain amount of energy that exists. This is known as the cosmological constant, which was first proposed by Albert Einstein in 1917. Einstein's original idea was that the cosmological constant could explain why the universe appeared to be static, even though his theory of general relativity predicted that it should be expanding or contracting. However, after the discovery of the universe's expansion, Einstein abandoned the idea. But in recent years, the cosmological constant has made a comeback as a possible explanation for dark energy. It suggests that the energy density of space is constant, and that's what's driving the universe's acceleration. Now, let's dive a bit deeper into dark energy and its properties. As I mentioned earlier, dark energy makes up about 68% of the total energy density of the universe. This means that it's the dominant form of energy in the universe, even though we can't see or detect it directly. To put this into perspective, think of a glass of water. The water represents the ordinary matter in the universe, including stars, planets, and gas. The ice cubes floating in the water represent dark matter, which is also invisible but has a gravitational effect on visible matter. And the air above the water represents dark energy, which is present throughout the entire universe and is causing the expansion of the universe to accelerate. The amount of dark energy in the universe is incredibly small, about 10⁻⁻29 grams per cubic centimeter. To give you an idea of how small this is, imagine taking a cubic centimeter of space and dividing it into 100 billion tiny cubes. One of these tiny cubes would only contain a few particles of dark energy. Despite its small amount, dark energy has a profound effect on the universe. It's responsible for the acceleration of the universe's expansion, which means that the distances between galaxies are increasing at an ever faster rate. The thing with dark energy is that it only seems to act on the largest scales of the universe, with the expansion of the universe a phenomenon that can only be measured by observing galaxies and other cosmic objects that are separated by massive gulfs of space in the order of millions, billions, and even tens of billions of light-years apart and away from us. And the greater the distance that separates these cosmic objects, the more rapidly they race away from each other. As a simple analogy for this, imagine drawing 3 spots on a deflated balloon, two close together and the other further apart. In this analogy, dark energy is the breath blowing into the balloon overcoming gravity, which is represented by the tension of the balloon's rubber skin. As the balloon is inflated, all 3 points will move away from each other, but the furthest point will move away more rapidly. This is like 3 galaxies, two close together and the other further apart, the latter of which is moving away faster because the space between it and the other galaxies, like the rubber of the balloon, is stretching, and more space means more expansion. Currently, scientists estimate that galaxies are getting 0.007% further away from each other every million years. So, what exactly is dark energy? Well, that's the million-dollar question. We don't know for sure what it is, but we do have a few theories. One theory is that dark energy is related to the vacuum of space itself. According to this theory, empty space is not actually empty. Instead, it's filled with a quantum field that creates particles and antiparticles that pop in and out of existence. This quantum field is known as the Higgs field, and it's what gives particles their mass. The Higgs field is thought to be the source of dark energy. According to this theory, the Higgs field creates energy that's evenly distributed throughout the universe, causing it to expand at an ever faster rate. Another theory is that dark energy is related to a new fundamental force of nature that we haven't discovered yet. This force would be repulsive, meaning that it would push objects away from each other. It's possible that this force is related to the force that causes the expansion of the universe to accelerate. So far, we don't have any direct evidence to support either of these theories. However, scientists are working hard to find new ways to study dark energy and hopefully unlock its secrets. One way that scientists are studying dark energy is through experiments that study the cosmic microwave background radiation. This radiation is a remnant of the Big Bang and provides valuable information about the early universe. By analyzing the cosmic microwave background radiation, scientists can learn more about the properties of dark energy and how it affects the expansion of the universe. Another way that scientists are studying dark energy is through large-scale surveys of galaxies. These surveys use powerful telescopes to map the distribution of galaxies in the universe and study how they are moving. By measuring the distances between galaxies and how they are moving away from each other, scientists can learn more about the effects of dark energy on the expansion of the universe. Although we still have much to learn about dark energy, it's clear that it's one of the most mysterious and perplexing subjects in modern physics. As we continue to study it, we may unlock new secrets about the universe and our place in it. So that was all for this video. Give it a like if you liked it. Do subscribe for more amazing videos in the future.